ATM refers to what you would experience at sea level. Okay? There's gas molecules. If you're at sea level, this is what the force being exerted on you. That's why it's called 1. 760 millimeters of mercury refers to a barometer, which I'll show you here in a second.
Is that what that stitch is? I'm just kidding. Oh my god.
Okay, so a barometer looks like this. And what we're measuring
he's not going to know his answer, but just kidding, so.
I don't know, so is this part of our last so we
Alright, so barometer. Now, when the weatherman does barometer readings, barometric pressure, they use inches of mercury. Okay? So whenever you see, are we allowed to use inches?
No.
No, so we use millimeters of mercury. So if you're at sea level, there would be 760 of these millimeters of mercury. Okay, that's where that unit comes from. Then there's a famous scientist, Corelli, who 1 torr is equal to 1 millimeter of mercury. So you should know a torr and a millimeter of mercury are the same unit. Okay? A torr and a millimeter of mercury are the same unit. And you need to know this conversion here. These are the units that we're going to use for pressure. Now, what is your car tires built in? PSA, pounds per square inch, without these inches. Okay, we're not going to use pounds per square inch. I have the conversions here, and there's a couple of mastery problems where they make you convert. It's probably good to practice your conversion a little bit, so there may be 1 or 2 on there. Pascal is the international unit. Physicists like to use this a lot. They've got torr. Bars are used by meteorologists. They talk in terms of bars. Millimeters of mercury, and ATM are what we're going to be using. Here's the conversions form. You can look those up in Google or whatever. And if I want you to use those on the test, I'll give them to you. Okay? So this is just be practice. You should be able to do these kinds of conversions. We've done them a lot. This one you're going to use a whole bunch. Okay, so make sure you know it. Okay, so when we talk about gases, so pressure, then we have volumes. Volumes is the space taken up by the gas. We're going to be using liters and milliliters for this. And then we've got temperatures. We've got temperatures, which are going to be in Kelvin and Celsius. Okay? We measure in Celsius. That's what your thermometers are going to measure. But all gas solid calculations are done in Kelvin. You need to know that. All gas solid calculations are done in Kelvin. If you do a gas solid calculation in Celsius, you're wrong. Now you should know the conversion from Celsius to Kelvin. This is test 1 stuff. Celsius plus 273.15. Can you guys see that in the back? All right. Celsius plus 273.15 equals Kelvin. I gotta use just 273 most of the time, but we want to be, and we can add more decimal places than that if you want. I don't know, this goes out like 6 or 7 decimal places. At some point you're gonna cut it off. Okay, so you should be able to convert those two. So when you're doing gas law problems, you've got to be in Kelvin, but we're going to measure things in Celsius. All right, amount of the gas. We're going to do grams and moles. And then finally, gas density. Okay? Now, gas density is done a little bit differently. What's the unit of density normally? That's grams per centimeter cubed, or grams per milliliter, right? Okay, gas densities are almost always done in grams per liter. Okay, so just be careful when you're watching your units. When you see density, gases are done in grams per liter. That has to do with making certain equations easier to use. Yeah, right. Last time I did this, it was USB. Okay, so make sure you pay attention to these units because that's what we're going to have to work these problems in. Okay, so there's some assumptions that we're going to make when we're dealing with gas laws. And these are what we call the ideal gas law assumptions, or the kinetic theory of gases. And this is going to make math a lot easier for us. Okay? But it gives us pretty good data. So you're expected to know the kinetic theory of gases, at least the postulate of so. And just if you get the general gist of it, you'll be able to get it down on a test. All right, the first thing is that, hey, they're pretty small mostly. Okay, you don't see DNA as a gas. All right, they're small, simple molecules, and they have mass. We talked about, hey, you take a breaker, put it over the Eiffel Tower, the gases inside weigh more than the Eiffel Tower. Okay, these gases are in random, constant motion. They don't have a pattern. It's not like a planet rotating around the sun. They're random, they move rapidly, and they're constantly colliding with each other, and they're constantly colliding with the sides of the container. The other thing is that these things, collisions, are perfectly elastic. These collisions are perfectly elastic. What we mean by that is no energy is lost when the collision occurs, and they don't stick together. You probably did this in physics class if you ever had it, where you take trains and you hit them together and you figure out how much force is being exerted by the other object. And they always put the term in, assuming elastic collisions. If you've ever done a lab, they always put like a rubber bumper around it, and then they collide it. That's all trying to mimic elastic collisions, because if you don't, then life becomes much harder. Next is the interactions between them are negligible. So you don't have a nitrogen molecule being attracted to an oxygen molecule. Okay? They don't like go across the room and decide like, kind of get together or whatever. So, the interactions between them are negligible. That's important. Finally, the volume. Hey, there's a lot of empty space. You know that, you're in good shape. And finally, the kinetic energy of these gases is dependent upon the temperature. The kinetic energy of these gases is dependent on the temperature. Because the higher the temperature, the faster they move. The faster they move, the more kinetic energy is exerted on the side of the container. So, in kind of summary, you need to know they have mass, they move in random motions, they have elastic collisions, the interactions are negligible, and the distance, there's lots of space in between, and kinetic energy is dependent on temperature. So we make some assumptions on all that, and it makes life much, much, much easier. Okay, so there's a number of laws that help us describe the behavior of these particular gas laws. And the first one we're going to cover is Boyle's. Now, Boyle's only deals with volumes and pressures. That means all the other variables we talked about are held constant. So here's our variables we talked about, ignoring density here, this is kind of physical property. But what we're going to do is when you describe gases in their completeness, you need to do all of these. We talk about pressure, volume, temperature, amount. If we're only talking about pressure and temperature, that means the volume and the amount must be held constant. So we're talking about changing. What happens when we change pressure and temperature? Okay? And hold the volume constant. So for example, we've got a container, and we keep the gas in the same container. Okay? And we keep the same amount of gas throughout the experiment, but we change the temperature. What happens to the pressure? That's what Boyle's is telling us. Okay? So, in Boyle's law, we're just going to deal with pressures and volumes, assuming the amount is held constant and the temperature is held constant. All right, Boyle's is an inverse relationship. Okay, so pressure and volume is important that you know that it's an inverse relationship. So here's my pressure, here's my volume. Now P2, V2 means that we have some kind of initial pressure, then we have some kind of initial volume, and then it changes. And it's an inverse relationship because if I take it and I increase, and I set this to some kind of number, let's make up a number like 16. Okay? If pressure goes up, what must the volume do in order to equal the same number? It's got to go down. If you don't see that, 8 times 2, 16. If I make 8 a bigger number, well, that's got to drop in order to equal 16. That's called an inverse relationship. That means as we increase one variable, the other variable has to go down, and vice versa. So let's imagine a clown car. Okay? And we've got 20 clowns stuffed in a car. And they have perfectly elastic collisions. They're constant motion. They're moving randomly. They're squiggling, wiggling, what do they got to do? Trying to move around this car. So the pressure's high on the side of the container. Now I put them in a football stadium. What happens to pressure? Down, right? That's what's going on with gas molecules. Okay? As you increase that volume, pressure drops. Because the amount of clowns has not changed. And the clowns are at the same temperature. Okay. The point being, yeah.
So the volume is not the number of molecules.
Volume is how much space they occupy. And they're always going to take fill the container in space. All right, so as I increase one, the other drops. That's Boyle's law. And we represent it with this equation here. Okay, we can graph Boyle's law. So here's some pressures and volumes, and we do a graph. This, as you can see, it's an inverse relationship. Now, I know I can't write on the board. So you get some kind of curve like this when I do my pressure versus temperature. If I have pressure 1, so we'll call this P1, volume. So then I have volume 1. If I increase the volume, make it a bigger number, and I go to V2, what happened to my pressure? It goes down. That's an inverse relationship. Okay? So that's represented by here. Why it curves out is you can only increase the volume so much for your break containers and stuff like that. So that's why I get that curve. Okay, to get a straight line, what you can do is take pressure and take the inverse of one or the other. And then you'll get a straight line. I'm not going to do anything like that, but I think you do that in lab. You might take the inverse of pressure to get a straight line. But if you just graph pressure versus volume, you get a curve like this. Anyway, what I want you to know is that as we increase pressure, volume drops, or as we increase volume, pressure drops, vice versa. They're inverse. That's going to be the opposite direction. Boyle's law is why we can breathe. Okay? Gases move from greater pressure to lower pressure. Is that right? If it wasn't true, then I could take a balloon, hold it in my hand, and it would inflate itself. Is that what you observed? No. So you have a balloon full of air, you release it, right? And it goes from greater pressure to lower pressure. That's how gases move. Okay, well, the same thing, your diaphragm is a muscle that helps with breathing, but Boyle's law helps more than your diaphragm because your diaphragm only has so much strength. And what happens is if the atmospheric pressure is greater out here than in your lungs, then air will flow from here into your lungs. If the pressure in here is greater than the atmospheric pressure, then it will come out of your lungs. So by decreasing the volume of your lungs, what should happen to the pressure? Decrease volume, what happens to the pressure? Increases. If it increases enough, the atmospheric pressure in your lungs is higher than outside, and you breathe out. If I expand the volume goes up, what happens to pressure? Goes down. Then the atmospheric pressure is greater than the pressure in your lungs and the air goes in. So by expanding, that's why people have a hard time breathing in different atmospheric pressures, is because their diaphragm is not used to expanding and contracting lungs like that. And so as you increase the atmospheric pressure or decrease it, you get harder to breathe because your diaphragm isn't used to that. It's muscle, right? Okay, so, and if you want a little video, you can click here. You can't click it. If you go to my website. Little video that shows this actually in play. Okay, so, Charles' law. All right, Charles' law. Charles' law deals with volumes and temperatures. That means we're keeping what constant? Pressure and amount. So the pressure and amount must be being kept constant. We're dealing with Charles' law. It's nothing but volumes and temperatures. Charles' law is a direct relationship. Charles' law is a direct relationship. So I got volume, got temperature. I'm going to set it equal to, say, 16 again. Now, if volume goes up in value, what must temperature do to equal the same number? If you can't see that, take 32 divided by 2. 32 becomes a bigger number, then 2 has got to be a bigger number if you're going to equal the same value. So, as one increases, the other increases, and vice versa. If one decreases, the other decreases. So a classic example, something like this, is take a balloon and put it in the freezer. Or leave it in your car on a day like today. If you buy a balloon and leave it in your car a day like today, what happens? Smaller. Your temperature decreases, what happens to the volume? Decreases. Charles' law in action right there. Okay? If you take a balloon and you put it in the oven, we're talking hang it in the middle of the oven. What's going to happen to it is it's going to get bigger or smaller. It's going to get bigger. Okay? This is how hot air balloons work, for example. This is all Charles' law at play. Well, no, it's going to shrink a little bit. It's just the property of the nitrogen. Or you're filling, the molecules are closer together, so it probably varies by less. Questions on Charles? Okay. So, Charles' law, if I just take some volume and I decrease it, my temperature changes. So, for example, have you ever seen these gas cylinders? This big. See people fill balloons out of them, right? We've seen these things before, right? Full of gas, right? It's actually full of liquid. Because as we change the volume, what's going to happen to the temperature, and vice versa? And the pressure. And the answer is it gets colder. And what happens is you end up with a bunch of liquid. If you were to actually, if you could do it quick enough, okay, or if you turn a container upside down sometimes. I don't know, you've ever seen this with canned air? Turn it upside down. Don't do it. What comes out of it? Water. Yeah, liquid, right? What's happened there is you have these relationships mean, and what I'm trying to pressure here is that pressure and temperature and volume are all related to each other. Okay? And when you see those cylinders, you're like, how can this thing be at room temperature but be a liquid and still be a gas? And the answer is you've messed with its pressure and volume. All right, so Charles, though, deals with nothing but volumes and temperature. Charles' law is how we get absolute zero. So if we graph volume versus temperature, here's just a set of points. So I took some temperature and volume measurements, and it comes out to be a linear relationship. If I change the conditions with the volume and temperature, it comes out to be linear. And then I extend that line. It goes to one point. Guess what that point is? Absolute zero. To reach absolute zero, which is negative 273, right? To reach absolute zero, what does my volume have to be? Zero. Can we have zero volume? Have gas? Therefore, we can't reach reach absolute zero. Okay? We get close. We got really close. But you're going to have to get down to single molecules, perfect crystals, all kinds of stuff, and they haven't been able to do it. Theoretically, your volume has to be zero. That has to do with entropy, which you'll learn about in 7. All right. Questions on that?
Yeah. What are you saying about that one?
Okay, then we have Gay-Lussac's law. And I wrote this purposely different. Sometimes you'll see B1, sometimes you see PI, it just means initial. So P1, B1 is the same thing as PI, VI. Okay? So don't let that throw you off. This means we start at some condition, then we change. Alright? Gay-Lussac's law is also a direct relationship. Gay-Lussac's law is also a direct relationship. What do we hold constant? Volume and amount. So if I hold it to a constant again, works just like Charles' law. If I increase one, I increase the other. If I decrease one, I decrease the other. Have you ever seen pressure cookers? They're like coming back in vogue. You get like electronic ones, like crock pots. Yeah. Pressure cooker, you know what a pressure cooker? Like 6 of you. You know what a pressure cooker is? Okay. So, do we have a fixed volume? Right? Does the amount of substance inside change once we seal it? No. As I increase the temperature, what happens to the pressure? It goes up. If the pressure goes up, what happens to the temperature? It goes up. So in a pressure cooker, what's happening? You're cooking with higher temperatures. That's why it takes. A lot of restaurants use this all the time. If they want to whip out a roast beef, right, you think they actually put it in the oven for 8 hours or whatever it cooks a roast beef, 6, 7 hours, whatever, slow cook it? No, what they do is they slap that sucker in the pressure, boom, 30 minutes, roast beef done. Okay? And it makes it nice and tender with all the juices and everything else. I'm not a pressure cooker salesman, I'm just saying. I ain't know one. Alright, anyway, this all works off of Gay-Lussac's law. This is also why the wind blows. We'll assume, we're talking global scale here, the amount of gas at any given point is roughly the same. There's an average amount of gas in the air. Okay? We're talking macro scale here, so it's about average. We've got oceans giving off gas, we've got humans, we've got CO2, it's all this balance. Okay? And so we'll assume that the gas is relatively the same, so we can drop its variable out. Its amount is about relatively the same. Is the Earth's surface heated the same everywhere? So you're saying that one part of the Earth is a different temperature than another part. If that's true, is there pressure differences? And if gas is at higher pressure than a gas that's at low pressure, what's going to happen to it?
It's going to move to low pressure.
Go from high pressure to low pressure, right? Hence the wind blows. The wind blows because of uneven heating of the Earth's surface. Okay? That's why the weatherman is, or woman, is completely obsessed with barometric pressure, and you don't care. Like, what is it about? I don't care about barometric pressure. And they have like this chart, and there are all kinds of pressures everywhere. And you're like, who cares? Because they're trying to predict where this air is going to go, right? And it's going to go from greater pressure to lower pressure. So they spend a lot of time measuring pressures everywhere. Because then you can figure whether something's going to come your way or not based off its pressure. Okay? this uneven heating of the Earth's surface. So questions? Okay. We could combine all this together into the combined gas law. This is the one that you need to know, and if you know this one, you kind of know the other ones. This is the one you need to know, and if you know this one, you kind of know the other ones. So the way I memorize this, because you need to know this, the way I kind of do this is I know the combined, and then I think boils, no temperature. Okay, boiling water, right? Okay. But he doesn't deal with it. So boils, no temperature. If you remove temperature, you have whose law? Boils. If you remove pressure, you have whose law? Charles. If you remove volume, who do you have? David Sachs. Okay? So if you just remember Boyle's no temperature, and you remember Charles no pressure, you'll remember all those gas laws. Now sometimes you'll see this, but not very often, you'll see in here also, which has to do with Avogadro's law. I'll talk about here in a second. But normally we don't change the amount of moles when we deal with gases a whole bunch. So a lot of times this is just left out of here. As an option. But we know that we have to hold the moles constant, otherwise it messes things up. All right, so that's the combined gas law. This is going to help you solve a whole bunch of problems. So here's all this reviewed. Okay? Here's all my different laws. Here's all the stuff held constant, inverse, direct relationships, so on and so on. All right, some other knowledge. One is this term called STP. You need to know this. I'm not going to give it to you on a test. As a scientist, we try to keep variables constant so we can measure what's affecting what. So when we do chemical reactions, many times we will keep things constant so we can study the effects of other things. Because science always works, you should learn this back in the day, that we hold all the variables constant but one, we vary it, see what happens. We hold all the constant variables again, we pick a different one, we vary it, see what happens. Okay? And so one of the ways that's done is a thing called STP, which means standard temperature and pressure. And it equals 1 atm at 0 degrees Celsius or 273 Kelvin. So 0 degrees Celsius at 1 atm. You need to know that. You're going to see it in problems over and over and over and over again. You need to know what STP means. They're not going to state it out for you every time. Standard molar volume just means we have 1 mole, same conditions. Okay? So standard molar volume just means we have 1 mole of the substance at the same conditions. Avogadro. Remember him? Well, he was famous for gas law stuff. That's where he came up with Avogadro's number. If you take any gas, doesn't matter what it is, and you have 1 mole of it at 1 atm at 0 degrees Celsius, that's STP, right? Molar STP, if you include the mole. It will have a volume of 22.4 liters every time. And the number of molecules it will have is 6.02 times 10 to the 23rd of it. That's where Avogadro got it from. And so no matter what gas he took, if I put it under those conditions, I got the same volume. Then he said, well, if I'm getting the same volume every time, then you have to have the same number of molecules every time. And he calculated it. And so that's where Avogadro's number comes from. Now the density varies because it's a different gas. Its mass varies. But under standard molar volumes, you always have the same volume, same temperature, atmosphere, moles, same kind of molecules. So I expect you to know what STP means. All right, let's work some problems. Now I can do these until I'm blue in the face, But in reality, you just need to practice these. There is a worksheet under course content in addition to practice tests. Plus, there's the whole bunch of mastering. Okay? You're going to have, probably at least one of every type on there on the test. You need to make sure you can do these. You think I'm going to label it Boyle's Law? Okay, so then you're going to have to figure what law you have. All right, so watch this. The pressure of a combustible mixture in a cylinder in a motorcycle is 0.980 atm. The volume is 246 milliliters. The piston decreases the volume to 24.1. What is the pressure at pressure in ATM at the point which no change in temperature has occurred? Okay, here's the deal. You're doing these problems. Listen to my words. If you see a change occur, notice that I'm going from this many mils to that many mils. So if you change it, see a change in volume, a change in pressure, or a change in temperature, that's going to be the combined gas law. Every single time, pull the combined gas law out. Then eliminate variables that are held constant. Again, if you see a temperature change, a pressure change, or a volume change, then you're going to use this gas law right here. The only thing is, sometimes you get to eliminate variables. So, what are we holding constant here? Temperature. How do you know that? Did they mention temperature anywhere else in the problem? And we always have those three things affecting. Okay? Always those three things interplay. If they don't happen in the problem, it must be being held constant. So, that means that if it's the same value here, it's the same value here. And if I divide both sides by the same number, does it change it? Therefore, I can drop this out. Whose law is this? Boyle's law. So now I'm just going to put in the variables. It says I have a gas that starts at 0.980 atms. I have a volume of 246 milliliters. We're going to equal some new pressure we don't know, but its volume is going to be 24.1 milliliters. That's how all these gas law problems are going to work. You're going to know every one of the variables but one of them. And then you solve the thing you don't know. Okay, there are two rules, Brian High rules, for solving gas law problems. First of all, you need to make sure your units are the same on both sides before you start sticking in your calculator. All right, I have milliliters here, and I have milliliters here. Is that good? If I have ATMs here, what is the unit that's going to come out over here? ATMs. So make sure that your units are the same on both sides. The next is, thou shalt not work any gas law problem in Celsius. All these are derived using atmospheres. That's why we have to do that. So all the temperatures have to be in atmosphere. They cannot, not atmosphere. All the temperatures have to be in Kelvin, because that's the way they were derived. So I'm going to divide over 24.1 milliliters. Pressure in the unit ATM is 10.0 atm. Alright? Not too bad. Now these can be worded 100 million different ways. As you see, I'm going to go through here, word them all kinds of crazy ways. The key to victory, to know that you're using the combined gas law, is look for those changes. When you see those changes, that's going to be combined gas law time. And we have other laws, so it's important that you pay attention to that one. Thou shalt not work any gas law problem in Celsius. And that, of course, means degrees. What is the volume of the balloon at this temperature? Okay. Was there a change in volume, temperature, or pressure? Temperature went from 30 to negative 10. As soon as that happens, boom, write that on your piece of paper. Now, what variable is not mentioned here? Pressure. And many times they will say the words constant pressure. But since all of these are variables that we have to use, it must mean that we're at a constant pressure, because it's not mentioned in my problem. So therefore, pressure goes away. Whose law we left? Charles' law. Now I'm going to put in my variables. I notice my volume starts at 3.25 liters. My temperature is 30 degrees. Well, some new volume, I don't know. But we went to negative 10 degrees Celsius. Good to go? Don't do it. Or I can go Lord of the Rings. None shall pass. Don't do it. You cannot work any gas law problem in Celsius. It must be in Kelvin. So I'm going to add 273.15 to each one of these values. Now, a lot of times I just use 273, sometimes 273.15, and it can make a little bit of difference in your answers, but I'm never going to have a test question where the answer is 40.1 and one is 40.2. Okay, they're going to be distinctively different. All right, so I need to mathematically solve this. Chemistry is over. Now, if you can't do this, you can blame your math teacher. All right, what I do on this is I just cross multiply. So I'm going to multiply these across and these across, and it doesn't matter what side I put them on. So I have V2 times 303.15 equals 325 liters times 263.15 K. And you could have had these over here, that over there, it doesn't matter. As long as you get them on the same side of the equation. That's cross multiply. Now it looks kind of like the other one. So now I divide over. K's cancel. I'm left with unit per liter. What do you think? Not too bad. Questions? All right. Sachs law. One of these. A sample of gas in the rigid container at negative 23 degrees Celsius is at a pressure of 500 torr. What temperature in degrees Celsius will it be necessary to change the pressure to 800 torr? Okay, did the pressure, temperature, or volume change? Yeah? If that's true, then write this equation down. If that's true, write this this down. See if there's any variables you can drop out. Since it's a rigid container, what does that mean? That means my volume stays the same. Another way you know that is, did they give you a bunch of volumes before and after? Okay, that means that this must be held constant and dropped out. All right, so now I'm going to put in my values. So I start at 500 torr. My temperature is negative 23.3 degrees Celsius. I'm going to equal some new pressure, 800 torr. I don't know that difference. So it's always the same. Get them all, solve the thing you don't know. How are we doing on units? Torr is the same on both sides. That's good. If they weren't, you got to make them both same. Other, are we allowed to look at Celsius? No. So I'm going to add 273 to that.
Would you need to change it because it's asking for the temperature?
Absolutely. Thou shall not work. Any gas law problem. Good observation. Thou shall not work any gas law problem in Celsius. Okay, so solve this. What do you think I'm going to do? Let's cross multiply. Okay? So I'm going to cross multiply. It doesn't matter which one I put on what side. I'll mix it up this time. Cross multiply them. Now on a test, if let's say this is a written question, the only thing I require really is you show this. After that, I don't care what you do. All right, as far as solving it. You don't need to show me any work. You might be able to do that in all your calculator, whatever. All right. Now I'm going to divide over by 500. What's my answer going to be? In what unit? In Kelvin. Did they ask me for the answer in Kelvin? No, so my calculator is 400 out. Okay. And you know what's going to be on the test? The answer 400. And you're going to go, well, thrill of victory. Yet the agony of defeat. You've got to start watching units in science. Okay? So I need to get this to Celsius. So I've got Celsius plus 273 equals 400 K. My Celsius equals 127 degrees Celsius. So make sure you're watching your units. I'm not trying to be mean to you. I'm just going to tell you what I'm doing. Yeah. That's right. You end up with negative volumes, which don't make any sense. So we need to derive everything using absolute zero. Otherwise, Charles ends up with negative volumes, which doesn't make any sense. If you can show me a negative 10 liters, I'm all for it. I'll show you how it gets complicated. All right, questions on that? All right. This is one where we can't eliminate anything. Okay. A gas sample is heated from negative 20 degrees to negative 57 and has a volume increase from 2 liters to 4 liters. If the initial pressure is 1.25 atm, what is the final pressure? Do we change temperatures, volumes, or pressures? Yes. As soon as that happens, I write down the combined. Now I look for things I can eliminate. Are there temperatures given? Are there pressures given? Is there volumes given? That means I can't get rid of anything. I got to put it all in there. So I start with my initial pressure. We start at a volume of 2. Our initial temperature is 20, negative 20. Some new pressure we don't know. Our volume goes to 4.
0.5.
Hard to see. And then finally a temperature at 57 degrees Celsius. All right, a couple things happening. So our volumes are the same unit, liter, that's good. If they're not, they need to be the same. Our temperature is the same unit, Celsius, We're good to go? I'm trying to, there's going to be like 10% of you, 15% of you who just don't care about Kelvin. And you're going to solve this in Celsius, and you're going to see an answer. And then you're going to be really mad. All right, I can't work that in Celsius, so I need to change those. Okay, so now I can get busy and work. So how am I going to solve this? I had like 20 answers last time when we did it again. Right across multiply. Nothing's changed. Right across multiply. So I've got this P2, 4.50 liters. 253K. Right? Same thing. No matter how many variables we have. Equals 0.125 ATMs, 2.00 liters, and 330K. All right, so now I'm just going to divide over, like I did last time. I just had 2 things to divide over. What unit am I going to come out in? ATMs, because my liters cancel, my Kelvin cancels, and I'm left with ATM. Watch. Okay. Watch those. All right. what volume in liters will this gas occupy at 80 degrees Celsius and 800 torr? Okay, anytime you see STP, your brain needs to replace or know what those units mean. This gas, when it starts out, is at 5 liters, right? But it's also at STP, which means what? 1 atmosphere at 0 degrees Celsius. You just need to know that. So it's telling you more information about the gas than they're giving on with the word STP. So anytime you see STP, just cross it out, write 1 atm, 0 degrees Kelvin. Are we changing temperatures, pressures, or volumes? Right? 1 atm to 800, 0 degrees to 80 degrees. So we're definitely changing. Therefore, we pull this out. All right, I plug in values. STP, so what's our pressure? 1 atm. Volume, they tell us, 5 liters. Temperature, 0 degrees Celsius. Equals some new pressure, 800 torr. Some volume we don't know, but our final temperature is 80 degrees Celsius. All right, so what's our issue? Yeah, can't handle Celsius. What's our other issue? Okay, so we have 2 different units going on here. Okay? So you need to know now the easy part, the easy one, would just to put 760 millimeters of mercury here, right? Because a millimeter of mercury equals a what? Torr. But I'm going to be a rubber. Give us practice.
Don't do it.
I don't want torr in my problems, I want ATMs. But you can work this in torr, it doesn't matter. The only thing that matters is Kelvin and same units. So 800 torr, there are 760 of these torrs for every 1 ATM. My units cancel out, and I'm left with ATMs. You'll get the same answer no matter which way you do it. All right, so